right, so as advertised, let me just kind of look at the calculus of hyperbolic functions for just a little bit here. And I think this is a nice review of some of our techniques. So I think the fundamental thing is what? I mean, what are the hyperbolic functions, right? So fundamentally, we take e to the x, we write 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. That's just a sneaky identity, but it's useful. So I've just added 0, right? And so 1/2 plus 1/2 is 1. But this first function is hyperbolic cosine, and the second function is hyperbolic sine, right? And fundamental properties, cosh is even, sinh is odd. The next thing I would do, just taking a walk down memory lane, is to notice that e to the x times e to the minus x, right? Well, that's equal to e to the 0, which is equal to 1, right? But it's also equal to e to the x, which is cosh x plus sinh x, right? And e to the minus x, because hyperbolic cosine is even and hyperbolic sine is odd, that's cosh minus sinh, right? And so when we multiply those out, what happens? We get cosh squared minus sinh squared, right? So that tells us that cosh squared x minus sinh squared x is equal to 1. So yeah, that's kind of the fundamental identity for hyperbolic sine and hyperbolic cosine. Now, if you take a look at that identity, there's two corresponding identities we can get for what are the reciprocal functions, right? So the reciprocal functions, hyperbolic secant, which is 1 over cosh. We have hyperbolic cosecant, which is 1 over sinh. And we, of course, have the hyperbolic tangent, which is sinh over cosh, right? And there are identities for these, right? So if you take the fundamental identity here and we divide by cosh squared, what do we get? If we divide by cosh squared, we get 1 minus sinh over cosh squared equals to 1 over cosh squared, which is to say 1 minus hyperbolic tangent squared is equal to 1 over cosh squared, which is hyperbolic secant squared, right? And we can also derive, that's one of them. What's the corresponding identity for, like with cosecant? We divide by sinh squared, what do we get? We get hyperbolic cotangent, which I haven't even defined, right? Minus 1 equal to this guy. Okay, so these are, and of course you know that there's similar derivations we can do for, sine, cosine, tangent, secant, cosecant, right? So the algebra here shouldn't be unfamiliar. Now, that I've sort of exposed us to the basic algebra here, how about calculus? Well, we know that d dx of cosh x is what? We have 1/2 e to the x plus e to the minus x. So when we first encountered this, we were kind of fresh on our differentiation, but now it should be a piece of cake, right? This is derivative of e to the x, which is e to the x. And then chain rule says that that's minus e to the minus x, right? the minus 1 comes with the chain rule, differentiation of the minus x. And of course, that's sinh, right? So likewise, the derivative of sinh is cosh, right? Let's go ahead and work out the derivative of tanh. How are we going to do that? So we're looking at, well, sinh over cosh prime. Right? So quotient rule says that that's sinh of x differentiated times cosh x minus sinh times derivative of cosh divided by the denominator squared, which here is hyperbolic cosine squared, right? But what do we get? We get, let's see here, cosh. I'll do it in yellow. So this is cosh x, this is sinh x. So we get cosh squared minus sinh squared, which we just derived as 1, right? So the numerator works out to 1. We get 1 over hyperbolic cosine of x quantity squared, which is to say hyperbolic secant squared of x, right? So there you go. Just like the derivative of tangent is 1 over cosine squared, which is, of course, secant squared, right? And we also derive that from the quotient rule. Now, another thing we could do is we could look at, well, let me look at the derivative of hyperbolic. I'm going to look at the derivative of hyperbolic cotangent a little different, just for kind of an experiment. So this is d dx. I'm going to write it this way. This is d dx of, that's cosh over sinh, right? So I'm going to do cosh of x times 1 over, I'm going to look at it this way, just for the sake of illustrating tools we have, all right? So I'm going to look at a hyperbolic cotangent as a, a product of functions, right? And so if we do this, what do we got? We use the product rule, right? What's the derivative of the reciprocal function? So just a reminder, d dx of 1 over u is what? It's d du 1 over u times du dx, right? But what is d du of 1 over u? It's minus 1 over u squared, right? It's minus 1 over u squared. So this is a chain rule for the reciprocal function. We do minus 1 over the thing squared times the derivative of the inside function. So applied to 1 over sinh, we've got minus 1 over sinh squared times the derivative of sinh, which is cosh, right? And so what do we have? We have, this is sinh, right? Sinh over sinh is 1. So this is 1. And that's what? Minus, it's cosh squared over sinh squared, which is hyperbolic cotangent squared. Right? But remember, what is 1 minus coth squared? 1 minus coth squared is it's minus cosecant squared, hyperbolic cosecant squared. Right? So just to, I mean, could you do this with the quotient rule instead? Sure. Right? Do you have to do it this way? Absolutely not, right? Is this the smart way to do it? I don't know. Kind of depends. Let's look at another example. So sometimes I like to put this kind of example on the next test because it just helps me to see if students are kind of awake or not. So here's let me show you a couple of examples on this theme. Differentiate e to the x cosh x. Right. Now, I mean, let me make it a little bit worse. Times e to the minus x, right? All right, at this point, it's kind of like, oh, man. So if I was to have to do product rule, I mean, there's a couple different ways you can go here. So you guys, give me some options. What should you do if you have this? Should you just differentiate? I mean, you know the triple product rule, so you could do it, right? But that would be unwise, because what should you do? Well, I mean, I guess let me write a suggestive step here. These are just multiplications, right? So we can rewrite this as e to the x times e to the minus x times the hyperbolic cosine of x, yeah? What's e to the x times e to the minus x? It's 1, right? So this is really the derivative of cosh. So, I mean, just because you know the product rule doesn't necessarily mean that you should automatically treat it as a product, right? I mean, we should always be thinking about basic rules of algebra for simplifying things, right? But you need to be careful. Don't make up rules of algebra that aren't there either, right? So like here's an example where if I'm going to differentiate, say, the square root of cosh squared x plus sinh squared x. So some students would try to do algebraic simplification. They might try to simplify this to cosh plus sinh, but this is wrong, right? Because the square root does not have this property. It's not true that the square root of a sum of two things is the sum of the square roots. There is actually no way to simplify this, right? You differentiate. And to differentiate this, I use the chain rule. So this is my u, right? So I do 1 over the square root, twice the square root of, u, and then times du dx, which here is d dx of cosh squared plus sinh squared. So that's 1 over 2 times the square root of u, 2 cosh sinh plus 2 sinh cosh. So you notice there's a 2 everywhere. We can cancel it out. And what we have is 2 times sinh cosh divided by the square root of cosh squared plus sinh squared. That is kind of like a straight down the middle problem I would expect any B student in my class to do without like a lot of effort. Like this is something you should be able to differentiate on the next test, for example. Okay, so I've showed you we can use quotient rule, right? We need to know the chain rule just to differentiate e to the minus x at the base of things here. Can you guys tell me, how about the graph? Like, let's talk about the graphs. Hyperbolic functions. Let me just remind you. So here they are. So first of all, cosh, it's, just like this, right? Sinh, something like that, right? So here we have y equals to cos x. What's dy dx equal to? Sinh x, right? And does that make sense? Like, so sinh, notice here, it looks like this, right? So sinh is negative for negative x, sinh is positive for positive x. And that's how cosh works, right? It's decreasing until 0, then it's increasing, just like sinh is positive and negative correspondingly. Likewise, if we have y equals sinh, well then dy dx is cosh, right? Now cosh x is greater than or equal to 1. So in fact, the slope of the sinh function is at least 1. Like the most shallow slope this thing has is actually at 0. That's y equals x. That's the tangent line to sinh at 0. I know it has slope 1 because cosh of 0 is 1, right? But otherwise, sinh is everywhere increasing, right? So sinh is an everywhere, a strictly increasing function. Cosh is sometimes decreasing, sometimes increasing, right? So we also talk about inverse hyperbolic sine, inverse hyperbolic cosine, right? So notice that, this is basically it. Inverse hyperbolic sine is the inverse for the whole sinh, all right? There's no need to restrict hyperbolic sine because it's literally just the whole thing, right? But on this one, it's customary. See, this doesn't pass the horizontal line test, right? So to find an inverse, you have to restrict the domain, and you restrict it to this piece. So technically speaking, inverse hyperbolic cosine is equal to, actually, it's the hyperbolic cosine restricted to 0 to infinity inverse, if you want me to be technical. That's the part of the hyperbolic cosine that the inverse hyperbolic cosine is by custom defined for. And this reflects into the following identities. Hyperbolic cosine of inverse hyperbolic cosine of, let's say, y is equal to y again, and inverse hyperbolic cosine of hyperbolic cosine of x is equal to x again. So my point is that that's for 1 less than or equal to y less than infinity. You don't have to put the infinity there, you know, and for x greater than or equal to 0. That's the extent of those identities. Hmm? What, this and that? This is and. That's just and. So for y is an element of 1 to infinity, and x is an element of 0 to infinity. That's the, what that is the domain and the range of the function hyperbolic cosine restricted to 0 to infinity. So the domain of the function is the range of the inverse function and vice versa. Now for inverse hyperbolic sine, it's easier. You just have sinh of inverse hyperbolic sinh of y is equal to y, and inverse hyperbolic sinh of x is equal to x again. And this is for all x and y in the reals. So this one's much easier to discuss because inverse hyperbolic sine, hyperbolic sine is everywhere increasing, so we can define a global inverse, and we don't really have to make some kind of ad hoc restriction of the domain of the function to make an inverse. We sometimes forget about this, but we cannot help but avoid this baggage with trigonometric functions, right? We talk about inverse tangent, inverse sine, inverse cosine. These are actually all local inverses. We're talking about sine, cosine, and tangent restricted. Sine's restricted to minus pi over 2 to pi over 2. Cosine's restricted to 0 to pi. And, wait a minute. Yeah, 0 to pi. And inverse tangent is actually the inverse of tangent restricted to minus pi over 2 to pi over 2. These conventions are reflected when you take calculator values. You'll find that that's the interpretation you have to adopt. Of course, logically speaking, you could find inverses for the trigonometric functions with respect to other restrictions of their domain. Y equals to tangent of x is, so for this I find it useful to write the following formulas. This is e to the x minus e to the minus x over e to the x plus e to the minus x, right? And that's just sinh over cosh. And I've canceled out the halves, right? Sinh over cosh, I canceled the halves out. And so, great. If you write, there's two formulas here that I find very useful. I've told this to you guys before, but I'll tell it to you again. So this is e to the 2x minus 1 over e to the 2x plus 1. And it's also 1 minus e to the minus 2x over 1 plus e to the minus 2x, right? So I'm just multiplying. These three formulas I find useful. They're useful to me because from those I can see that the limit as x goes to infinity of inverse hyperbolic, excuse me, I said inverse, I meant just hyperbolic tangent. What's it equal to? And what's the limit as x goes to minus infinity of hyperbolic tangent equal to? See, the key observations here are that the limit as x goes to infinity of e to the 2x, or e to the minus 2x rather, are 0, right? And the limit as x goes to minus infinity of e to the 2x is 0. So these two results are super useful when you look at the yellow expressions right below them, right? Because you can easily see that as x goes to infinity, that goes to 0, and that goes to 0, so we're left with 1. On the other hand, as we go to minus infinity, well, these two guys go to 0, and we're left with minus 1 over 1, which is minus 1. And so for these reasons, I understand that asymptotically, the hyperbolic tangent is stuck between these two horizontal asymptotes, right? And how do I know it doesn't cross them? Like, let's see here. How can I gain confidence that like that really is the graph? Right. These are those. Fair enough. But my question is, how do I know that the graph really looks like that? What other things could we use calculus? We could use calculus to understand the derivative and the second derivative. That would tell me about the concavity. And well, the increase, decrease, and as well as the concavity. That would give me further confidence in my graph, right? So let's do that. What's dy dx here? I'll write y prime because I'm kind of not a lot of d. We worked it out a second ago. The derivative of tanh was, yes, hyperbolic secant squared. And what can you tell me about that? Right? Yeah, it's 1 over cosine. I'm going to erase these limits up here. They're kind of cramping my style. And what can you tell me about 1 over, what can you tell me about this? 1 over hyperbolic cosine of x quantity squared. Can you tell me anything about that? Like, tell me numerically, what's the largest that can be numerically? See, if I ask you when's a fraction largest, right, you should understand that you could trade that question for the question, when is the denominator smallest, right? if the numerator is fixed. In this case, it is, it's 1. When is cosh x smallest? Right there, right? So if you think about it, the hyperbolic secant is largest when x equals to 0, right? So what I'm trying to say is this is greater than or equal to, what, 1? No, it's less than or equal to 1, right? Less than or equal to 1, because hyperbolic cosine is greater than or equal to 1. So, okay, great. How about y prime prime? I'll do it up here because I'm kind of out of space down there. That's kind of a pain, isn't it? I'm not sure about this one. What's the derivative of hyperbolic secant squared? It's what? 2 hyperbolic secant of x times the derivative of hyperbolic secant. What is the derivative of hyperbolic secant? Yeah, I don't remember right offhand. I'm going to write that as 1 over cosh, right? So that is a reciprocal, so we get minus 1 over cosh times sinh, right? So I have twice 1 over cosh for this guy, and then minus 1 over cosh squared of x times the sinh of x, the chain rule. So altogether, what do I got? I've got minus 2 sinh x over cosh cubed, right? So where is this function concave up and where is this function concave down? I'll draw it out bigger down here. So we just figured out that y prime prime is minus twice the hyperbolic sine of x over the hyperbolic cosine of x cubed. We know that hyperbolic cosine is positive, right? In fact, it's larger than 1. So if you think about the SIGN of y prime prime, it's only going to be 0 if sinh is 0, right? So there's only one potential inflection point here, namely 0. And if you think about it, this denominator is always positive, and the numerator, it's minus 2 sinh, right? So when sinh is negative, we get minus and minus, which is plus. So lo and behold, we've got plus. We got pluses, we got minuses. So it's concave up over here, it's concave down over there, which is what we have graphed. Concave up, concave down. And if those are concave up and concave down, it stands to reason that, well, it's more than that, right? Also, is this function, it's also increasing everywhere, right? Y prime is less than or equal to 1. But I can also say that, I mean, I kind of buried the lead here. So 0 is less than y prime is less than or equal to 1. So the rate of, like, the increase, the slope of the function is between 0 and 1. So there's no way this function can, like, I know it's not 0 because hyperbolic secant's not 0, right? So that means there can't be a turning point for the graph. The graph has to look like this, is what I'm trying to argue. So do you need to do all of this to see that? I don't think so. But the more you know, the more confident you can be about your graphing, yeah? Now, how about the inverse function? So I'll give you this example. What's d dx of inverse hyperbolic tangent of x? So what's our go-to method for calculating the derivative of an inverse function in here? So let me remind you. Step number 1, y equals what we're trying to differentiate, right? Step number 2, take the function of both sides. In this case, hyperbolic tangent. So I get hyperbolic tangent of y is equal to the hyperbolic tangent of the inverse hyperbolic tangent of x. Let me use some red chalk here. Remark. Inverse hyperbolic tangent of x is not equal to 1 over tangent of x. Do not think this. Remove this from your thinking. Okay, this is not what it is. That is the reciprocal function of tangent. That's what we call cof, the hyperbolic cotangent. I understand, like, you're like, but, this is, minus the hyperbolic cosecant of x squared, right? So that's your notation. Well, it's an inconsistent notation. Beware of it. The inverse means inverse function. The square actually literally means algebraic squares. These are not consistent notations. You have to be aware of this. So I'm just telling you, now you've heard it. Someone's still going to do the opposite thing on the test or final. It's just a fact of it just happens. But okay, so tangent of y is x. Now we do what? Differentiate implicitly, right? Derivative of tangent, we just figured out was hyperbolic secant squared. But I have to multiply by the derivative of the inside function, which here is dy dx. That's equal to 1. That gives me dy dx. 1 over hyperbolic secant squared. What is hyperbolic secant squared, though? In terms of hyperbolic tangent. Yeah, at the start of class, we derived 1 minus tangent squared equals hyperbolic secant squared. So this is 1 over 1 minus hyperbolic tangent squared of y, which is what? So the derivative of inverse hyperbolic tangent of x is equal to 1 over 1 minus x squared.
So we use the x like that.
Yeah, well, up here we have tangent of y. Yeah. Let me use a less invisible color of chalk. Like the red you guys can see in here just fine, right? But on the video, it's almost invisible, you know? Oh, I'm sorry. I tried, but yeah, it doesn't matter too much. Basically, what I did was, I could summarize. The video essentially says, in the notes, Taylor's theorem is proved. This is what it says. It says that if you use a kth order Taylor polynomial, the error in using that is captured by basically the next thing you didn't use, evaluated at some point in the interval. That's essentially all it says. And so if it's a problem, just ignore that video and just go straight to like the doc file. I have put links in that should make it pretty easy for you guys. Hopefully. If not, come talk to me about it. Now, my question to you is, does this make sense? Why is it that there is what is it about inverse hyperbolic tangent that's making something fun? Look at this. This is what? 1 over 1 minus x times 1 plus x. Does that make sense? What's so special about x equals to plus or minus 1? Why is plus or minus 1 appearing as places where the derivative of inverse hyperbolic tangent is not defined? So my question to you really is another way I could ask this question would be, what is the domain of inverse hyperbolic tangent? The domain of inverse hyperbolic tangent, right, is equal to the range of hyperbolic tangent. What's the range of hyperbolic tangent? -1 to 1, right. We saw that in our graph. So, in fact, this feature of the derivative blowing up, right, having a divergence, it's happening at the edges of the domain, right? So apparently, the graph of inverse hyperbolic tangent has vertical asymptotes, places where the derivative goes to infinity at the boundary points of the domain. And if you go back to the graph of hyperbolic tangent, this is not especially surprising, because the graph of hyperbolic tangent, remember, did what? It had horizontal tangents, right? And so, like, this is kind of a general theme for when we're talking about, inverse functions and such. When you look at a function, the graph of a function versus the graph of its inverse function, you kind of expect to see the roles of x and y interchanged in the graphs. And so, what's going on here is that, the graph of inverse tangent, it's got actually vertical asymptotes at plus or minus 1, right? Versus up here we had, y equals 1, y equals minus 1. Those are horizontal asymptotes of the function. Here we had vertical asymptotes for the function. And, what does it look like exactly? If y is inverse hyperbolic tangent, we just figured out that dy dx y prime is 1 over, what was it, 1 minus x squared? 1 minus x squared. What's the concavity here? What's y prime prime? Well, how about we do chain rule, right? Think about this as like 1 over u. So it's minus 1 for 1 minus x squared squared times the derivative of the inside function, which is minus 2x. So the second derivative here is 2x over a quantity squared. So what can you tell me about that? Where is this positive? Where is this negative? What's the possible point? There's only one point of inflection here. It's 0 itself, right? X equals to 0, this is 0. And then it's negative for negative x, it's positive for positive x. So if I was to graph the sine chart for the second derivative, it looks like this. So it's concave, concave down over here, concave up over here. So apparently the graph must look something like concave down, concave up, like that, right? And I don't think I've quite done that justice, because what's the slope of inverse tangent at 0? I made it look like the slope is 0. Am I right? I don't think I'm right. What's y prime of 0? It's 1 over 1 minus 0 squared, which is 1, right? So if I did this graph like right, I should be like going through the origin at a line with slope 1. So you kind of have to, it's not exactly connecting the dots, it's something like that. But there you go, there's the graph of the inverse hyperbolic tangent. We know the slope should be 1 because, we also know that it goes through the origin because tangent of 0 is sinh of 0 over cos 0, which is 0 over 1, which is 0. And that says the inverse hyperbolic tangent of 0 is also 0, right? So yeah, I know it goes through the origin. But I also know that it has slope 1 at the origin because I have the derivative, right? Okay, so my idea for this lecture was just I thought it would be a useful exercise to just go back and just do a case study on how we can use calculus to understand the derivatives of hyperbolic functions and, you know, also to look at their graphs. There's more we can do with differentiation. There's another thing I should show you. Do you guys know that there's identities for hyperbolic functions? Like, let's see here if I can, I'm trying to think of a convincing way to derive it. I'm not sure what's the most convincing way to derive what I'm about to derive. Let's see here. Let me try it this way. If we do hyperbolic cosine of A times hyperbolic cosine of B, what do we get? Like, do the algebra, what do you get? We get e to the a plus b plus e to the a minus b plus e to the, well, minus a plus b plus e to the minus a minus b. So what does that equal to? So what I'll do is I'm going to take these two guys, put them out here. And I'll take the other two, put them over there. Oh, that's where my blue chalk went. Look, I couldn't find my blue chalk. I don't know at what point I dropped it on the ground over here, but it's there. So this is like a factor to minus out. That's minus a, this one, minus a minus b. So this guy is that guy actually.
I do have a question.
Sure.
Can e raise a plus b and e raise negative a plus b cancel each other?
Oh, they don't cancel each other, but that has a name. Like this is hyperbolic cosine of a plus b. And the other one, right? This one is hyperbolic cosine of a minus b. So, okay, so I mean, this is something you can do. So, you know, we can look at specific cases, right? Like, so consider A equals to B equals to X, right? What does this identity give you? It gives us that hyperbolic cosine squared of X, right? Equals to what, 1/2? Hyperbolic cosine of 2x, right? What's the x minus x is 0. What's the hyperbolic cosine of 0? Hyperbolic cosine of 0 is 1. So this is plus 1. So we get the identity that hyperbolic cosine of 2x is in fact equal to, let's see here, 2 hyperbolic cosine squared of x minus 1. Now, at the moment, I haven't done any calculus, right? I mean, that's just straight algebra, right? But what's cool is if you know one identity and you know calculus, you can find more. Differentiate this identity. What happens? d dx, we get 2 sinh of 2x by the chain rule equals to 2 times 4 cos x sinh x. Right? So in other words, the hyperbolic sine of 2x is equal to twice cos sinh. So that's kind of neat, right? There's other things you could do. Like, let me just take a step out of hyperbolic land here for a second. You guys know the adding angles formulas, right? Adding angles formulas for sine and cosine. Like, for example, how's it go? Sine of a plus b is sine a cosine b plus cosine a sine b, all right? So let's let a equal to x and b equal to b. So sine of x plus b is what? Sine of x cosine of b plus cosine of x sine of b. Differentiate with respect to x, holding b constant. What happens? What do you get? You get cosine of x plus b. Chain rule says derivative of the inside function is 1. Fine. Differentiate the other side. What do you get? We get cosine x cosine b minus sine x sine b. That is the adding angles formula for cosine. So if you know one, you can derive the other by differentiation. This is a powerful idea, right? Do you guys know the adding angles formula for tangent? Ever thought about this? Like, what's the tangent of a plus b? See, what you do is okay, so that's sine of a plus b over cosine of a plus b, right? So how's that work? Well, we know that that's sine a cosine b plus cosine a sine b divided by cos a cos b minus sine a sine b, right? And then you have various options to simplify it. If you want it back in terms of tangent again, or tangents again, the thing I would do, well, I'm really trying to break that blue chalk, if it is resistant. So just multiply this by 1 over cos A cos B, and what happens? When you multiply that by that factor there, let's see here. So the first, so you have to multiply through, right? When this hits that, you get sine over cosine, cosine over sine, you get tangent A, tangent B. When this hits that, well, cosines cancel. You get sine over cosine, you get plus tangent B. Oh, I'm an idiot. I'm wrong. So cosine B canceled cosine B, right? So I get I was like, this is not very symmetrical. Why do I get 2 tangents and then 1 tangent? That doesn't seem right. It's because I made a mistake. So tangent A plus tangent B, right? And downstairs, so this just multiplies through, it gives you 1.
That's close.
Yeah, and then this one is, It's sine over cosine A, sine over cosine with the b's. So it's tangent A, tangent B. And there you go. That's the adding angles formula for tangent that you probably used in your trigonometry course. In fact, your instructor probably derived this for you. Let me be optimistic and say that you had to leave the room. You had to use the restroom or something. Perhaps you were sleepy that day. Something obscured your attention. This happened in class. I'm not blaming. It's not. I'm not going to blame you, and I'm not going to blame the teacher. We'll just blame society or circumstance or something. So you know, I don't think I've ever done this, but fun idea. What would happen if you like put A equals to X and leave B alone? What happens? Put A equal to X and leave B as a constant. You could differentiate this, right? And what would that give you? That would give you an identity for secant squared X plus B, right? And it would be unpleasant. Of course, there's another way you could derive that one. You could just do 1 over the cosine identity squared. But relating those two expressions might actually reveal new and interesting trig identities. Anyway, you can combine the algebra and the trigonometry, you know, with calculus to learn new things and to discover old things. It's a powerful tool. Now, I know you guys have a formula sheet for your test, right? So some of what I'm telling you is not terribly interesting at the moment. But later in your life, you may face like a math field test or something, right? Like you have to take a test that's timed, and most of these tests now, basically they involve mastery of calculus. So the more you know, the better you can do, right? And so like learning ways to remember all of these things at once, it does have a payoff in those kinds of standardized tests. But I would argue they're just fun also, but I realize I'm in the minority. So you guys had questions about homework? I'll stop blathering on about this stuff here. We still, I think, have 20 minutes or so. 20 minutes? I can't see. Oh, I'm sorry. We have more like 15 minutes. I'm being optimistic. We have 10. 12 minutes. I started late, though. I'll stay here after class if you guys have questions. But so you mentioned that the cubic function. So as you guys know, this is a review week, and so, you know, hopefully we'll have, what am I looking at this? Which number was that? So were all the L'Hopital problems work out okay? Oh, this one. This is one of those kind of Build-A-Bear problems, you know? I was intentional in trying not to give you guys any L'Hopital problem, which was too tricky. There are some nasty, nasty L'Hopital problems out there. I have tried my hardest to select homework problems for you guys on L'Hopital's rule, which are pretty cut and dried. You should be able to solve them with a minimum of effort. So I hope that was. I hope it worked out that way. You said it did for you? Like, yeah, the limits at the end of this? Good, okay. Good. So you're asking me about problem 120. So I'm happy to work it here for you. And because we're missing so many people, I'll collect this Wednesday because, you know, I really think it's best for you to have finished most of it today. That's good. I think you'll do better on the test because of that. You know, x squared plus cx plus d. So that was our cubic function. And we're supposed to find a cubic function that has a local maximum of 3 at -2. Select, basically. So the question is to select A, B, C, D such that what? F of minus 2 equals to 3 is local max. Anything else I know? Oh, it's got a local minimum value of 0 at x equal to 1. F of 1 equals to 0 is local min. Aha. Well, all right. So we know two critical numbers is what I would say from this, right? Now, there could be more than one answer here. It's possible, I suppose. I'm not sure right offhand. But we know this much, right? We know f prime of minus 2 is 0. And we know that f prime of 1 has to also be equal to 0 from, what is it? Was it Fermat's theorem? It said that if the derivative exists at a point and it's at a local extrema, it must be the case that the derivative is 0 at such points. That was, I think, Fermat's theorem, right? But it's also just common sense that if you have a local max or min, you got to be at the top or the bottom of the hill. And if the derivative exists there, it's got to be a horizontal tangent. All right, so df dx is what? 3ax squared plus 2bx plus c, right? And, all right, so what do I know? I know that that's 12a minus 4b plus c equals to 0 from star. And from star star, I get what? I get 3a plus 2b plus c equal to 0, all right?
3ax squared 2bx is plus 8a.
So x equals to minus 2, and x equals to 1. What else do we know? Ooh, we know f of minus 2 is 3. And we know that f of 1 is 0. So we also know these two things, right? So f of minus 2 is 3 is minus 8. I'm plugging them into f, right? Minus 8a plus 4b minus 2c plus d equals to not 0, but 3. And f of 1 is, well, that's a plus b plus c plus d is equal to, well, 0. Now, you guys haven't had that class yet, but I'll tell you this. Anytime you get to the point of having as many linear equations as you have unknowns, there's a good hope that you found a solution, because once you have like 2 equations and 2 unknowns, you can solve. 3 equations and 3 unknowns, you can find a unique solution. 4 equations and 4 unknowns, you can solve. Now, how do you solve? That depends on what you know, right? But I think for you guys, at the moment, like elimination is the name of the game here. So if I call this, let me give these names, 1, 2, 3, and 4. I can take 1 and 2 and I can subtract those equations, right? 1 minus 2 gives me what?